Hey there, UMS engineering students. Welcome to your pre-class explainer for week 2 of KS 23003. We're going to tackle a really cool concept today that's going to be a massive time saver for you later in the course. We're talking about signal symmetry. So, to get us started, let me ask you a kind of weird question. When you look in a mirror, what do you see? Well, your left side becomes your right side, and your right becomes your left, right? But you're not suddenly upside down, your top and bottom stay the same. Believe it or not, signals have a very similar kind of symmetry, but instead of swapping left and right, they swap the past and the future. And this is exactly what I'm talking about. On the left, a mirror swaps your physical sides. On the right, a signal's time reversal, which we write as x of minus t, does the same thing, but with time. It takes everything that happens in the future, for all time t greater than 0, and swaps it with everything that happened in the past. This whole idea of time reversal is the absolute key to understanding everything else we're about to do. Okay, let's get into it. First up, we're going to define the two basic types of signal symmetry that you're going to see over and over again. So first, we have what are called even signals. A signal is even if its time-reversed version, that x of minus t, is exactly the same as the original signal, x of t. It's like it's a perfect mirror image of itself, reflected around that vertical axis where time equals 0. An absolute classic example you'll see in your textbook is the good old cosine wave. And the other type? Well, that's an odd signal. A signal is odd if, when you time reverse it, you get the negative of the original signal. So x of minus t equals minus x of t. A good way to think about it is that it's mirrored and then flipped upside down. And you guessed it, the perfect example here is the sine wave. Okay, pay close attention to this one. This is huge. It's a crucial rule that's going to save you so many headaches. For a signal to be truly odd, it absolutely must be 0 right at the origin at t equals 0. So if you're ever doing a problem and you calculate an odd part that isn't 0 at t equals 0, you know you've made a mistake somewhere. It's a brilliant little self-checking tool. So, we've got the definitions down. Now let's build on that and put together a simple test we can use to classify any signal that gets thrown at us. Here it is, your 3-step foolproof method. First, you take your signal, x of t, and find its mirror image, x of minus t. Second, you just compare that result to the original you started with. And third, you make the call. Is x of minus t exactly the same as x of t? Great, it's even. Is it equal to minus x of t? Then it's odd. But what happens if it's neither of those? Well, let's find out. Let's take a really common signal from your course, this causal decaying exponential. That's x of t equals e to the minus t multiplied by the unit step function u of t. So we run the test. When we find x of minus t, we get e to the positive t times u of minus t. Now you can see right away that's not the same as what we started with, and it's not the negative of it either. So what do we call it? We classify this signal as neither even nor odd. And this brings us to a really important point. Most signals you'll actually encounter in the real world are just like that one. They're neither purely even nor purely odd. But, and this is the secret, every single one of those signals is actually built from a hidden even part and a hidden odd part. And that leads us to the main event, the decomposition formulas. These are basically the keys to the kingdom. They let us take any signal and crack it open to find those hidden symmetric pieces inside. And here they are. These two simple formulas are all you need. To get the even part, you take your signal, add its mirror image, and divide the whole thing by 2. For the odd part, you do the same thing, but you subtract the mirror image and then divide by 2. That's it. And the best part is, these work for continuous time signals with t and for discrete time signals with n. Okay, enough theory. Let's see how this actually works. We're going to do a step-by-step walkthrough of a classic example from your course material, breaking down the signal x of t equals e to the t. So let's follow the recipe. Step 1, find the time-reversed signal. Easy enough. If x of t is e to the t, then x of minus t is e to the minus t. Step 2, we plug both of those into our even part formula. That gives us the hyperbolic cosine, or cosh of t. Step 3, we plug them into the odd part formula, which gives us the hyperbolic sine, sin of t. So now we have our two components. But how do we know we got it right? We check our work, we just add our two components back together. And as you can see from the math right here, when you add cosh of t and sinh of t, everything simplifies out beautifully, and we're left with e to the t, our original signal. It works perfectly. We've taken the signal apart and put it back together again.
Okay, quick timeout. Let's talk about a really common mistake that catches so many students. When you're using these formulas, it is so easy to get caught up in the algebra and just forget to divide by 2. Please always double check that part. Also, when you're substituting minus t into a complicated expression, just slow down. It's not a race. Be careful with your signs.
All right, let's wrap this up. Here's your mission for this week. This is what you should feel comfortable doing before you walk into your week 2 class.
Before your lecture, make sure you can nail these 4 things. 1. Look at any signal and tell me if it's even, odd, or neither. 2. Use those formulas to actually calculate the even and odd parts. 3. Always check your work by adding the 2 parts back together to get the original. And 4. Know that simple, powerful rule by heart. An odd signal has to be 0 at the origin.
And I'll leave you with this final thought. What we've done today isn't just some random math puzzle. It's a massive shortcut. As you're going to see later in your course notes, understanding symmetry will save you a ridiculous amount of work, especially when you get to Fourier analysis. So my question for you is, how are you going to use this idea to work smarter, not harder? Think about that before class. I'll see you there.